All right, morning everyone. Thank you for joining us again on RC Design class. Very happy to start talking about the design lab. This is pretty new, okay? Uh, we're gonna wait for a couple of actually 1 minute. A little bit background of this design lab. Now, we have a structured concrete class, right? Reinforced concrete class. We do also have a construction materials class. Originally, the reason why we set up the design lab for the structure is that we're able to design a structure and maybe test it in the lab. But due to the COVID, that we have to shy back a little bit on the real testing side of it. However, though, the design concept of this shouldn't be avoided, right? So I just want to quickly introduce a modern steps, so to speak, of quick design methods of design buildings. All right. So it's less formal today, and I wouldn't say fun yet, but that's more relaxing. So just lay back and let's quickly walk through what is the design entail. Okay. So now let me share a screen. All right. So this is my YouTube screen. If you guys can see it. I'm gonna hit the play, and this is about a luxury modern concrete house in Trento, Italy, right? Uh, so concrete gave us an impression that usually it is pretty ugly, right? Pretty, how to say, old-fashioned. But on the contrary, this building is pretty modern and nice, and people use more and more of straight concrete for walls and interiors without any decorations and sidings. All right. So this has become very trendy, matter of fact. So we have more and more of concrete buildings erected, not only just for libraries, structures, that for public purpose, but also residential, all right, and also for small facilities institutes. Okay, so if you go to more suburb area, there are more availabilities in terms of construction materials, construction methods, and because of the natural resilience of the concrete and also the design aspect of the aesthetic, which means it's actually beautiful, people start paying more and more attention to concrete buildings. Okay. Now, there are also a lot of new design concepts populating these days. If you go to a residential market later when you graduate, find a job and buying a house, you see that people tend to like open spaces more, sunlights more, right? Span long span distances, right? So this requires us to have a better understanding of how to build or design a structure that have long span lengths, meaning beams and columns that can be integrated better, right? And in essence, I'm just going to drag, as you can see this, people are starting using precasting more and more, right? So they build the members and then they just put up together on site, right? So we no longer are in the traditional industry that it takes years and years to design. Everything is modulated. And you will be required to go on site and inspect some of the members and just do a quick hand calculation to check your design in comparison with the computer design, right? So that's what is required nowadays. Okay, so today I'm going to do like a 10 minutes quick walk of what if you were a structural engineer on site and what you will do in terms of beam design. Okay, so let me pause sharing on this and I'll post this YouTube. If you're interested, you go on YouTube, search for concrete modern structures, and you'll see a lot of buildings like this. Okay, but let's get back to the main topic at hand right here. Is that I prepare a short presentation, which I will also upload to the Canvas. So this is similar to what the YouTube video I showed to you. It's a more like origami type of structure building. And what does origami mean, right? Origami means folding a paper, right? It's a old ancient Chinese and Japanese paper art. That is, you can fold a paper sheet like this, right? In the middle of the structure, can you see it? Like this, to have a beams that have a different elevations connecting together. So simple folds like this in the structure is actually hard to do. But for us now, modern days, we can do it. And the beauty of that is that you can see that they create a more space, right? A staggered space between the lower floor and upper floor. So you have more maximized sunlight going through the shield of glasses and also have a more of a living space and activity space for the building. And on top of that, right, you have a beautiful landscape that you can lean onto to utilize the space right here. Okay, so this is from the architecture point of view. Of course, everybody's happy and we're all excited about it. But for us structural engineer, this become a problem, right? Become a problem because this beam is very hard to make, very hard to make. Okay, so what will be the criterions or what will be the challenges to make these beams? Simply because we want to make a slender or thinner section, right? Imagine if I have to make a bulky section that can take care of the weight of the building and take care of the live load, distribute the load on top of the building, it's going to be disastrous, right? And you notice that there's only very few columns, right, sticking through this, and this glass cladding does not take any load, right? So imagine you are a structural engineer, excuse me, and you were forced to go on site in the Monday morning, and you look at this building, and the guy just handed you a stack of sheets, said, "Look, Bob, go check the design for this." Okay, what will you do, right? And you take a look at the building and say, wow, this is complicated, right? But you say, no problem. You say, no problem, right? I can simplify it, right? So in my eyes as a structural engineer, quickly I can split them into three components. Number one, number two, and number three. Okay, now these three components correspond to the horizontal member here, an inclined member here, and another horizontal member here. Okay, now let me make more simplified assumption. Let's just say, you know what, the details of the connection, I don't need to worry about it right now. Okay, why? Because I can use computer later to check them, and I can do some sophisticated analysis to make sure that the connections are okay. All right. So as a structural member, the most important thing is you think of it, right? If an earthquake hits or a loading distributed on the beams, as long as this beam can stand and this beam can stand, I'm okay, right? I'm okay. Now I'm looking at number one and number three, these two beams. I say number three is more reverse loading because there has a bearings underneath it, might be, right? And then I don't know how I'm gonna design this. So I'm gonna leave this to senior engineer, right? So as a junior engineer, I pick number one to do a simple design for it, to do a simple design for it. Okay, so I go on site, I did this simple drawing. It's just a block, isn't it? It's a concrete block. I say that the span length is roughly 25 feet, and I have a concrete self-weight, 150 pounds per cubic feet. The live load, distributed load on top of it is 0.3 kips per linear foot. Okay, and if I put load on it, it's gonna sag and give me a deflection of delta at the middle span. Okay, and because now I have a more connection here, and you may not see it, but on the back of it has another connection in the other corner, so I can assume it's more fixed support rather than simply support condition. Okay, so this actually helps me, right, to restrain the deflection. Okay, now I look at this beam, I say, you know what, I can start analyzing it, right? So the total load is 1.2 dead, which is the self-weight of the concrete, okay, plus 1.6 live, which is given 0.3 kips per linear foot, okay? All I have to do is I need to find out how much moment the beam is experienced at the middle span, right? How do I do that? How do I do that? Right? You got to go back to the homeworks and to the problem we talk about before, right? Given the loading, right? Estimate the section size, right? Estimate the section size and do the self weight, do the live weight, the live load, and find out the maximum moment at the middle span for this fixed supported beam. All right. So once I find that, right, all I have to do is design for it, right? So how to do that? You refer to the chapter 4. We talked about design moment, right? VMM, right? How to design that for it. Of course, you got to provide a reinforcement and calculate the moment capacity, so on and so forth, right? So after the moment, we talk about shear, isn't it? So what would be the shear distribution along the beam? Will be the shear distribution along the beam for fixed support, isn't it? And then where's the maximum shear is going to be at the critical section, and how do I calculate the shear resistance? What type of stirrups I need to apply to resist that shear, right? On top of that, we said that the beam is going to sag, and even this fixed support two ends, right? What will be the deflection of that, right? Will it be smaller than L, which is the span length of 25 feet, divided by 200, right? Will it satisfy this criterion by ACI, right? If it's not, I have to put more reinforcement or make a bigger section to satisfy that, right? At the end of it, we also talk about bar size. What size bar we're going to use, what details we're going to use. right? So this sounds a lot, but it's just a checklist for me, right? So Monday morning, a sipping cup of coffee, and I look at this. I said, you know what? I'm gonna do all this, and I can say the member is safe, right? So for the sections, right, I start thinking maybe I can go to rectangular, maybe I can go to this T-beam, or I can go even to I-beam, right? Anything that makes my life easier, right? But there are some restraints. The width for the rectangular section has to be kept between 0 to 20 inches. The height has to be smaller than 30. For a T-beam or I-beam, the width has to be less than 50 inches. The height has to be less than 30 inches. So I have to work with my parameters. I need to design for the beam with this particular section constraints, right? But everything else are open game. What I can use to make the beam shorter, right? Make the width smaller. I win because I gain more space. Coming back to the architects, right? I gain more space in the buildings. So that is my driven forces. Okay, now this is a nice dream, right? And after a sip of a cup of coffee and 15 minutes of thinking and cooling down, I start to realize, whoa, that's a lot of work. That's a lot of work. I got to do the calculations, and to do this, I got to start selecting bars by assumption and putting in the bars and do all the calculation. If it doesn't work, and since it's doubly reinforced, I'm gonna be in trouble. I'm gonna keep doing it, never get a design out. That's impossible, right? But guess what? There are calculations. There are simple calculation tools. And these goes back to the answer to the previous question in the lecture. Someone asked me, say, Bob, can I program your equations into the spreadsheet, Excel sheet? Let the spreadsheet does it for myself. For example, a doubly reinforced section. How do I find moment? How do I find shears? Right? So I can simply encode everything, the equation encode everything into the spreadsheet, and I just punch in the number, and the spreadsheet will spit out the number I want to have. Right? So this is actually not a bad thoughts at all, right? So I'm going to share you a screen of a typical spreadsheet, okay? And this spreadsheet, I just downloaded online anywhere, right? I search for a spreadsheet for concrete beam design, and this just gave me an example like this, right? So we had this or similar like this in a design office, right? So what it does is that if you take a look at the spreadsheet, which I also upload to the canvas, that it give you details. What is the concrete weight? Is it normal? Is it light? And depends on that, use different lambda. Okay, what is exposure level? That determine the concrete cover, right? And straight gradient amplification factor, don't have to worry about that. We don't have that. Gamma, other factors, we don't have to worry about that. Combined loading factors, F prime C, for KSI, beta 1, 0.825, some of the number like that, right? Depending on different concrete strengths, so on and so forth. You see, we can actually code all our equations into a simple Excel sheet, right? So what the spreadsheet does for us is that you just need to input the section size, the parameters you need to use, right? And you can select, well, you can take a look at the table of these and select the corresponding bars, right? With different bar sizes and give you the different capacities, right? For example, this is the effective compressive zone size A, and C, actual compressive size, tensile strength to check what is the phi, right? Phi is my reliability factors, right? Strength resistant factors, zero point 0.9, 0.75, all that, right? And there are other things that we don't really worry about it, right? For example, maximum flexural stress, or all the durability factors, all these, we don't have to worry about it. But coming back here, I also have my phi right? And I may also have my shear. I also have my shear, VBC, VBS, so on and so forth, right? So these are very good tools you can use to speed up your process. So basically, you can determine a size for the bars, size for the section, bring to this spreadsheet and spit out a number for you. Okay, so that will help you to do the design. That will help you to do the design. All right. So this sounds more like a daunting task because a lot of things to do, right? But we're not asking you to do all of them, right? All you have to do is use the spreadsheet, right? I upload it to Canvas just like this. Make changes as you see fit. Make changes as you see fit. And just go back to this question here. Provide the reinforcement details and section sizes to resist whatever loading that subjected to the beam. And what loading? 150 pounds per cubic feet of self weight. And the live load is 0.3 kips per linear foot. So check your flashers, meaning moment, check your shear, satisfy the shear, check the deflection, make sure that it's smaller than L over 200, right? And come up with the smallest, come up with the smallest section, okay? Come up with the smallest section. And then that will be the optimum design. All right. So once you finish all these, right, you just need to provide a simple drawings. And I show some of the typical drawings I found online, right? 4 or 5 minutes, you can search a lot of things. And then you can see that what we need to do in a report, right? So the senior engineer asked me, say, Bob, just check the beam for me, right? So I take a whole day understanding all this. And end of the day, I provide a reinforcement detail for the beam for my hand calculations. So I have to make a report to my seniors, right? So what I would do, I say, problem statement. Okay, you took me to this building, right? I have more information about this building. You can search online. And you just stated this is more like a beam that we're designing for, right? And then what load, right? This has a dead load and a live load, okay? And then what member is a beam member, right? And what side, what section? This is the rectangular section, T-beam section, I-beam section, whatever you want to choose, right? And then I'm trying to find out what detail calculation, right? I'm using ACI 318 for this rectangular, so for this section, 0.1, 0.2, something like that. And I'm checking for flexure strengths, right? For flexure strengths and for shear, for deflections, that's all I'm checking. Flexure strengths, shear, and deflections, right? And I will also provide my detailed sections drawings, right? Say like, the bar size, the spacing, the details, all that. And on top of that, I will provide my spreadsheet as appendix, right? I say, look, this is my detailed calculation. You don't trust me? Go to the spreadsheet I use and check whether I made it right or wrong, right? So then the last references, which reference you use. If you use ACI, right? Now you use the spreadsheet I found online, right? Respect to the owner, we'll put him in the references, which I'll provide. If you just made a spreadsheet all by yourself, put your name on there, say, you know what, this is my invention. And also team member short bio. Okay, I'm going to explain about team member short bio. Okay, so this is going to be a group project. All right, so I set up to 4 members group, meaning that you can self-organize a group together, find 3 other close friends, put up a report together. Okay, but you can also be individual. You say, I have some genius ideas. I don't want to share with others. I'm just gonna come up with my own design, do the spreadsheet, and use it for my own pleasure later when I find a job in a consulting firm or department of transportation, right? You can do all that. It doesn't really matter, but keep in mind that the members should not be exceeding 4, right? Upmost 4 members, all right? And the due date is midnight before May 10th, okay? Midnight before. You can submit before then, but don't submit after that. You should have some time, right? Circle back why I need team member short bios. So I hope that through this project, you have 4 members, right? So roughly in the design office, I have some friends. We all go to lunch. We discuss about a project. So we found that some of us are best at these things, some of us best at the other things. So in a report, we always collaborate together. Someone does the 3D drawings, show the detailed reinforcement. Somebody do the spreadsheet. Somebody do the check of calculation by hand, and somebody type the report up, basic, organize everything. Okay, so that's why I said 4 members. So the short bio also help you guys to know each other, right? It doesn't have to be long. It could be one sentence. Bob is a assistant professor in civil engineering department. He does teaching, research, and the spare time he does also teaching, research, and there's no other things, right? So something like that is a boring, nice guy, something like that, right? Can put up there and you can see that. But most important for me is that when I find some errors in the reports, right? I take a look at the team members. I know who's who and trying to understand why there's error happens. So this is so-called the word accountability, right? Accountability. Just like the end of your projects, when you submit to the contract agency, you have to stamp on your personality on the report. Okay. All right. So that is the detailed report in tile. Some people might ask me, okay, what is the length for the report? It doesn't matter. It can be as short as 3 pages, but I will look for the answers, right? So I want more proper reporting format, right? Following the sequence. It doesn't have to be a lot, but it doesn't have to be too less. It has to be minimum amount of information. Give me the details. Give me the details. All right. Now, Grading and incentives. The project will be accounted as a regular assignment. That means it will blend into the 25%, and the total grades for this is 100 points again. So it's just like a homework. It doesn't worry a lot, isn't it? But there is a strong incentive that I'll pick the top two teams. I'll pick the top two teams. Okay. End of the day, once your final exam is done, these two top teams will get extra 2 points straight up to your final grades. Right? For example, if you average lump everything up again, you say, you know what, my final grades is like say 89, and I need to bump up my grades 2 points more to get a level A. You got it, right? I had 2 points there, you got A. So that's how it works for the design lab. Okay. All right. So I'm gonna shut up right now with all these introductions and welcome any question on the design lab. Anything, folks? Is it boring? Is it too long? Anything? Any question about it?
So are we using that building you use as an example, or finding our own building?
You mean the spreadsheet or this building as this one?
Yeah, is that the building we're using to design a member?
Okay, yeah. So you don't have to use this building. All I care about is that I have some constraints for the members, right? Has to be 20 feet in span length. Okay, can you see it? And then has to be a section of B width smaller than 20 inches, H smaller than 30 inches for rectangular section. For T-beam or I-beam, B has to be smaller than 50 inches. Height has to be smaller than 30 inches. Everything else open games.
Okay.
Yeah, all right. Anything else, folks?
So we're just designing the one beam then?
Yes, very simple. One beam, walk your way through from moment, shear, deflection, so on and so forth. And use that computation tool you can, okay? You don't have to use this spreadsheet. You can make spreadsheet yourself. Whatever way, make your computation fast.
Do we still need to do hand calculations for the problem?
You don't have to. You don't have to. You don't have to, okay? Because it would take a long time actually if you do hand calculations. All right, and it is a small context, meaning that I'll be looking for the smallest section. Okay, and the reason for that is that I want to have more space in my structures. Okay, any other questions, folks? Any other questions? All right, it might be a little bit boring project to you right now. And might be simple, but don't wait till the last minute, okay? Things can get quite complicated when you start doing it. Okay, this is structured job, sounds very easy, but when you start doing it, we see a lot of details coming out. Okay, so what we'll do is that we'll have no class tomorrow, Thursday, okay? But instead, I'm gonna sit there, well, in the Zoom link, 1 o'clock onwards, right? 1 to 2 o'clock, that hour, and with the TA, Sean there as well. We'll be there answering any question you come apart when doing this project together. If you have need more time to organize your team members, please do so. And just whenever you form the report, put your team members there. And if you have more questions, you can email me anytime you want. All right. Okay. Any other questions? All right. Well, I'm gonna upload all these informations into a folders called Design Lab onto the Canvas. Okay. And the other purpose or expected outcome out of this project is that end of the day, most of you guys will do a senior design lab, and you will see the similar process again in the senior design. Okay. So I hope this project will help you to build out some fundamentals for that. Okay, now I'm gonna stop recording and I'll stay here in case you have any questions or want to discuss with me about anything about this course so far. Okay, all right, thanks, and talk to you tomorrow, I guess.